Okay, we have a problem here where we have a 3 by 3 matrix and we want to know if 4 is an eigenvalue of the matrix. I'm going to use this definition of eigenvalue. Lambda is an eigenvalue of a matrix provided I can find a vector x so that ax is equal to lambda times x. So suppose I could find such an x. Then I could also write ax minus lambda x is equal to the 0 vector. Or A minus lambda times the identity matrix, that's the 3 by 3 identity matrix, times x is equal to the 0 vector. So in other words, I factored out the vector x. So what I'm looking for is a vector x that's a solution to this vector equation. So I want to know that that's only going to work if there's a value I can plug in here for lambda that will make this matrix singular or not invertible. So I want a non-zero vector x that satisfies this equation. That means that by the invertible matrix theorem, this vector, this matrix, A minus lambda I, would have to be not invertible. So I know that's going to happen when the determinant of this matrix is 0. So what I want to look at is the determinant of this 3 by 3 matrix. So that's going to be 3, 2, negative 3. I'm just going to copy the matrix A into here. 0, 3, 4, negative 1, 1, 5. And then lambda times the identity matrix is going to be lambda 0, 0, 0, lambda 0, 0, 0, lambda. So I want to take the determinant of that matrix, and if I just do that subtraction, that's going to be 3 minus lambda, 0, negative 1, 2, 3 minus lambda, 1, negative 3, 4, 5 minus lambda. So I want to take the determinant of that. So there are a number of ways I could do that. Let me do cofactor expansion across the first row. So that's going to be 3 minus lambda times the determinant of, remember I cross off the first column, first row. So times the determinant of 3 minus lambda, 4, 1, 5 minus lambda, minus 0 times some 2 by 2 determinant. I don't really care what it is. Plus negative 1 times the 2 by 2 determinant I get when I cross off first row, third column. So that's going to be 2, negative 3, 3 minus lambda, 4. Okay, so let's calculate this. So this is going to be 3 minus lambda. Here I'm going to get 3 minus lambda times 5 minus lambda minus 4. This is 0, so I don't care about it. I'm going to get minus 1 times 8 minus, and this will be negative 3 times 3 minus lambda. Okay, so here, if I multiply all this out, I'm just going to get a polynomial in lambda. That's called the characteristic polynomial. So let's do that. I'm going to FOIL this, so it's going to be 15 minus 3 lambda minus 5 lambda, that's minus 8 lambda, plus lambda squared, minus 4. Here I'm going to get minus 8 and negative 3 times 3 minus lambda. So this is going to be, I'm going to go ahead and, no, I can't do that. 3 minus lambda. Let me go ahead and simplify that. Lambda squared minus 8 lambda plus 11 minus 8 minus 9 plus 3 lambda. Let's multiply this out. I get a minus lambda cubed. I'm going to get a 8 lambda squared and a 3 lambda squared. That's going to be 11 lambda squared. For my lambdas, I'm going to get a minus 11 lambda plus 24. Let me try that again. Minus 11 lambda minus 24 lambda minus 35 lambda and plus 33. Here I have a minus 17. Here I have a plus 3 lambda. Okay, so this is just a bunch of algebra, multiplying out and simplifying, distributing and simplifying. So let's see, I get minus lambda cubed plus 11 lambda squared. Okay, minus 32 lambda, 33 minus 17. So that's 16. Okay, so this is my characteristic polynomial, and I'm wondering really just if 4 is an eigenvalue. Now, typically I would want to find all the eigenvalues, but here they're just asking me if 4 is an eigenvalue. So I've probably done a lot more than I really need to solve this problem, because I could have plugged in lambda equal 4 right away and just calculated that determinant and see if I get 0. But let's go ahead and plug in lambda equal 4 here. So let's call this thing P of lambda. And so if I plug in a 4 there, I'm going to get minus 4 cubed is going to be 64, plus 11 times 4 squared will be 16, minus 32 times 4, plus 16. That's going to be negative 64. I'm going to do this. I have 11 16s and another 16. That's 12 16s. Here, let's think of this as 2 times 16, that's 32, times 4. So here I have 11 16s. I'm subtracting 8 16s. That leaves me with 3 16s. And I have another 16, so that's 4 16s. Which all told is going to be 0. Negative 64 plus 64, so that's 0. So lambda equal 4 is an eigenvalue of A. I can be certain that if I plug in lambda equal 4 into this equation, that I can find a non-zero vector x that would satisfy this equation.